Hi, good morning. So I always worry at this point that you can't hear me, but hopefully the volume is good. So welcome to the ZP Developer Zone. So every Thursday at 8 a.m. we like to do a webinar for our ZP Developer Zone members. And
hi, good morning.
There we are. Sorry, that's just a bit me checking the volume.
At this point that you can't.
Yeah, so it's 8 a.m. It's London time. It's 8 a.m. It's 29th of April 2021, and we always do this webinar for our members at this time. So appreciate you guys coming along this morning, and I'll sort of basically jump straight into it. Now every week I do put this this up, because at ZP, we have this developer zone, and it's become very active with people who are interested in learning about biosensors, or are actually manufacturing biosensors, or are developing biosensors. So we have the developer zone where we essentially organize collaborations. At this moment, I know I've mentioned it already, but one of our ZP developer zone collaborators is actually in the UK at the moment. He has, there's a lot of restrictions on, but the guy has cleared the COVID-19 restrictions, and so he's now in the UK with us. So it does show that we do honour this whole term about collaboration. And sorry, just writing to some of the guys online. So we do these collaborations. We have the developer zone, we have the academy, and we do these webinars every week. So what I first want to do is just discuss. This is a little bit of news that we're going to do quite a large webinar on the 22nd of June 2021. I'll put this link up later on, but we're going to do a large webinar, and you're all welcome to obviously register for it. We're going to do it with USN, the University of Southern Norway. So that will be about biosensors for agriculture, aquaculture and food. I hope it should be interesting, and yeah, you can sign up for that large webinar that we're going to do on the 22nd of June. Now this the webinar that we do for the developer zone on the Thursday mornings is often driven by the forum. So if you're a ZP developer zone member, you can put questions in the forum, and either members of the forum will answer, or ZP will also answer as well. So this week we had two questions. One was about carbon electrodes, and the other one was about inline monitoring for microbes in water, in drinking water. I did appreciate the fact that the members on the forum are obviously now responding to questions from other members on the forum, and I want to encourage it because the forum, or the membership on the ZP Developer Zone, is easily over 100 people. So there's no way that one person knows all of the answers. And so if you think you have a good answer on something, feel more than free to respond, because that way then the questioner will get the answers quicker. And we can also at ZP respond as well, but it's nice to have the two responses, because then you can kind of weigh up, or you'll get twice the information, then you can kind of weigh up the decision or the response. But that said, appreciate you guys responding on the forum, and we'll sort of dive into the question. So if I just dive backwards, the question was really, do they need to polish or clean carbon screen printed electrodes? So that's the topic of the question. So what we're referring to here is these hyper value screen printed electrodes from Zimmer and Peacock. So if the question was, do I need to clean your gold electrodes? So at ZP we obviously have, commonly we have carbon, platinum and gold. We do electrodes that are in graphene, but my opinion on graphene is it's a material that's very popular at the moment, but it doesn't add a lot of value to biosensing. It's useful if you want to have intellectual property, and you want to have what they call freedom to operate, so you can write patents. So graphene is useful from a commercial perspective, but from a fundamental sensor perspective, it doesn't add a lot. But that said, so at Zimmer and Peacock, we have these carbon electrodes. We also do platinum, gold, and as I say, carbon. Now, do we need to polish carbon electrodes is the question. And the answer would have been, if you'd asked me, do we need to clean or polish gold electrodes, then I would have given you this answer. I would have said, at Zimmer and Peacock, we manufacture gold electrodes, and I always recommend that when people receive our gold electrodes, they actually clean them. And I'd actually recommend that a lot of screen printed gold electrodes, people receive them as is, but actually gold is really good at absorbing molecules and partially oxidizing its surface. So gold, if you ask me the question, do I need to clean my screen printed gold electrodes, the answer would have been yes. And this data here would have just shown you why. That at ZP, I think we do a really good job of manufacturing gold screen printed electrodes, and we make sure that they're in good condition before they actually ship. So here you can see that we've tested some of our gold electrodes. They weren't, we were testing them in ferricyanide. They weren't in good condition. And it's worth saying that, you know, we've done something like 50 tests here. So it's not like we've tested one electrode in a batch and said, oh, the batch is good. No, we've tested like 50, you know, which is, and the only reason we can do that is because we've got all these parallel potentiostats with parallel test rigs. So if the question was, do I need to polish the screen printed electrode? The answer is definitely yes, unfortunately, if it's gold. And it doesn't matter if it's a ZP electrode or a electrodes from someone else. And when I say polish, I should just say clean. We often just clean them in the gold electrodes in something like 10 millimolar HCl, something quite mild. So you can see here that we had some electrodes that were very passivated. We cleaned them, we retested them, and the majority of this population, there's a few outliers there, but the majority of these 50 electrodes, really, it shows you something about the reproducibility of our manufacturing. One of the biggest complaints, I think, with people who use screen printed electrodes is irreproducibility of the fundamental screen printed electrodes. I think this really shows you that I think we do a really good job on reproducibility on the gold electrodes. But the answer on the carbon is we just don't do it on the carbon, because I think carbon is actually more inert than gold, at least when it comes to passivation of its surface. So I don't like to say, you know, but the answer is we don't clean the gold electrodes based on experience, and we just haven't found the need to. It's not that we haven't looked. You know, you can see that we've done quite an in-depth study on the gold electrodes, and we always test what comes off the manufacturing line. The gold ones, yeah, they can be quite passivated, and we have to clean them. And then when we ship them, I still recommend that people do a cleaning on those electrodes. Now, I do have some links to sort of cleaning gold electrodes, and I will put that in the sort of description later on. So I'm actually now going to slightly extend, because the question was, do we need to polish do we need to polish carbon electrodes? Do we need to clean carbon electrodes? And the answer is no. I think they come from us pretty pristine, and carbon electrodes, as long as you don't put your fingers all over the electrodes and sort of put grease down from your fingers, they're pretty good. I just want to kind of now talk about, you know, how I would go about functionalizing these carbon electrodes to make them into biosensors. I think the first thing I would do is I would read this paper. I have to recommend it because I'm one of the authors on it. But the nice thing about the paper as well is it's free. So that, you know, I do like open source or journals that allow you to kind of access the material for free. So have a look at this paper. Now in this paper, they're using ZP carbon electrodes. They did a comparison with another supplier, but they basically said the ZP electrodes were pretty good. So what they've done in this, they've taken ZP carbon electrodes. The first thing they did is they actually did cyclovoltammetry on them. So if you were going to build or functionalize a carbon electrode into a biosensor, and you were doing it in a lab, and you're developing your process, then I would probably recommend, follow the paper that I've just brought up. Now in the paper, the first thing they did is they did cyclovoltammetry on it, probably, if I remember rightly, using ferrocyanide. It's a bit of a classic. Then they functionalized the surface. So this is a sort of polyaromatic, there's 4 sort of benzene rings, and then they got a linker molecule on it. Now what's interesting about this is when they functionalized the surface, they then redid the CV, cyclovoltammetry, on this. So they functionalized the surface, then they did the cyclovoltammetry again. And the peaks actually went slightly up, which is kind of unusual, because when you functionalize electrodes, often the signal goes down. But in this case, they've functionalized the surface with this molecule, and actually the signal's gone up. So it's either because of the functionalization or because the fact is cyclovoltammetry is slightly cleaning the surface. But recommendation is get your carbon electrode, do a cyclovoltammogram on it, make sure everything looks good about it, add the coupling reagent, do another cyclovoltammogram. The nice thing is you can follow this paper and just make sure that each of your steps kind of lines up with this one. Next, what they did is they now couple the antibody onto the surface. And for whatever reason, I don't think they did a cyclovoltammogram at this stage, which they should have done really, because I think the cyclovoltammetry would become a lot more distorted, because now you're putting, antibodies are proteins, you're putting a sort of quite non-conducting material onto the electrode, so that really will distort the cyclovoltammetry, but I don't think they did in this paper. The next thing they did is they blocked the surface for non-specific binding using probably BSA, bovine serum albumin. So they did that. Then they did a CV, and the CV is now quite distorted because essentially the ferrocyanide can't really get to the electrode, so it's undergoing a resistance, and that ends up distorting the cyclovoltammetry. So if we back up to the original question slightly, the original question was, do we need to polish carbon electrodes? The answer is no. If you ask me, do we need to polish gold screen printed electrodes? The answer would have been yes. I think the paper that I linked to on the previous slide is a good paper for anyone trying to functionalize carbon electrodes. It's quite simple. You can follow the strategies quite well. You can see that when we're functionalizing the electrode, we often use cyclovoltammetry. But that changes slightly then when we actually are going to do the analysis. So now let's do the analysis part of the paper. So now we're going to do the testing. So we functionalize the electrode with antibodies. The first thing we're going to do is add some reporting molecule. So often we use ferrocyanide. I should have put axes on here, but this is essentially a differential pulse voltammetry, and they're looking in the reduction regions, hence why the signal, the magnitude, don't worry about the direction of this. It's just because it's essentially doing a reduction. So, but it's the magnitude that we're interested in. Now the next thing that happens in this paper is that they add, so they get the initial signal, then they add in the HCG in this particular case. It blocks the surface. This is unusual. When they block the surface, the signal actually goes up, and that's, we're doing what looks like a blocking assay. So when you block something, you'd expect the signal to go down. And but what's happened is the magnitude of this signal is actually increased, and in that case, I don't absolutely know, but it could be electrostatic attractions are actually allowing the redox reporter to get to the surface. So it's quite, I won't say quite unusual, but we have seen it a few times where it's a blocking assay, so you'd actually expect the signal to go down, but in fact in this case, when you get the binding, the signal went up. And it wasn't just once, it was kind of every time. So it's quite useful in some ways because the magnitude of the signal goes up with concentration. So yeah, Phil, thanks Philippe for the comments. You're right. We do try to, we've got a nice comment on YouTube. Yeah, we do try to kind of, it's in everyone's interest really for the world to have better biosensors. And when I say, it's in our interest at ZP, it's in academics' interests, it's in startups' interests. And I think it's the reason that at Zimmer and Peacock we do these kind of videos is because what's good for society is good for us as individuals, I think, is one of our kind of philosophies. So this paper is an easy enough paper to follow, and if you're using Zimmer and Peacock hypervalued carbon electrodes, follow the paper. But what is interesting is when we're functionalizing the electrodes, we're using cyclovoltammetry, and I would say it's just a habit. Cyclovoltammetry is quite quick and simple, but when we're doing the analysis in the paper, we're actually using differential pulse voltammetry, and I'll comment on DPV, differential pulse voltammetry, in a minute. But we get a magnitude that increases with the binding, so it's good. Well, we're happy with that, and that's the original data from the paper as well. So just some comments about what methods to use if you're doing these kind of binding or immunosensors. This is really a form of immunosensor. A comment: square wave voltammetry is a good method for analysis on these kind of immunosensors. Differential pulse voltammetry is pretty good. And at ZP, absolutely said it before, but actually the method that's working the best for us these days is electrochemical impedance spectroscopy, EIS. I am biased. This is the potential stat that we're using. It's from ZP, so I am biased on that. So you can use other potential stats, of course. But what I like about EIS is this: you get so much rich data that you can go through the data and find that feature in your data that is most indicative of the analyte of interest. So with impedance spectroscopy, you can construct an equivalent circuit. You can have your there's lots of elements in that equivalent circuit, and one of those elements might be particularly proportional to the concentration or the concentration of the molecule of interest. Sorry, I'm just saying hi to April. So I'm going to slightly divert a little bit, and I know I did a demonstration of Djuli EIS before, but I just want to emphasize that one of the things that Philippe was saying, it's nice that Zimmer and Peacock puts out this material, but what we're really doing as well is I think we're trying to help in a more wide way as well, because one of the things that we're working on is Djuli. So Djuli, if you go to knowledge base, you click on Djuli, you're going to find a description of Djuli, and Djuli is an online database that allows you to upload electrochemical data. It works particularly well with technology from Zimmer and Peacock, which we call Anapot and Anapot EIS. It also works well with PalmSense, so a lot of people have PalmSense potentiostats, so you can upload that kind of data. Now what I'm going to do is I'm going to do a demonstration of Djuli for EIS, but if you want data to play with, then there's some EIS data here and you can download it. What I'm going to do now is I'm going to go into Djuli. So for example, let me just change screens. So if you're trying to get into Djuli or trying to create an account with Djuli, just click here, create an account. Now I have an account on Djuli, and I did a demonstration last week. I'm going to do a demonstration this week. So what I want to do is I want to just deal with EIS. So what I'm going to do is I'm going to go to, I'm going to upload some data. So you can download this data off our website. But I'm going to upload it now off my computer because I previously have downloaded it off the website. A little slow. All right. So that's now uploaded. So the reason I've got to this point in the webinar today is because my argument is if you're using carbon electrodes, that's great. You can turn carbon electrodes into immunotype sensors, that's great. If you want to analyze them, use square wave voltammetry, differential pulse voltammetry. A favorite of ours is EIS. If you want to start playing with some EIS data, then Djuli is free online. You can create accounts. You can even get demo data off us. And if you've got the demo data, upload it. And then I'm just going to show you, and I have done this before, but I just want to kind of emphasize, because eventually I know that Djuli is free to use, and we know we're all the time we're working on it, trying to make it better. So I'm not trying to tell you that this is like, a finished, let's say, thing, but I'm just going to show you the raw data. So I've just uploaded the raw data, and you can see here that we have magnitude versus frequency, so a Bode plot, and we have the Nyquist plot here. So I've uploaded some data, and when you look at the legends here, some of this data is at 0 nanograms per milliliter, some of it's at 75 nanograms per milliliter, 50 nanograms per milliliter. So we have data as a function of concentration. The next thing I want to do now is I want to analyze the data. It's an interesting question, actually. Bishaf is asking if we use this, should we be acknowledging? Yeah, it's a good point. It would be nice to acknowledge, because I think if it's free, it's nice to be able to tell other people, about it. So, yeah, if you could, that'd be great. But it's a good question. We've never really thought about it. So, if we go to tools, I'm just going to do a circuit fitting. Now, like I say, I would consider this really a work in progress. It's something that we're still working on, because I just want to kind of show you. I just want to grab something out of my notes, so forgive me for a second. So what we're doing is we're getting to the circuit fitting. The circuit that I'm actually going to use is this particular circuit here, and I'm going to grab this piece of code here. When I say code, it basically says R1, so resistor 1 is in parallel with resistor 2, which is in parallel with a Warburg element, which is W here, that's in series with that R2, and then it's all in parallel with Q1, which is a constant phase element. So the one thing that's lacking from Djuli at the moment is the ability to draw in the circuit element. We say draw, but we haven't completed that module. So I'm going to paste in the circuit that I know works for this, and then I'm just going to fill in. There's two things that we need to complete on this. We need to be able to draw in it, and we need to then allow the software to actually automatically guess some of the values. But in this case, we haven't completed that part of it, so I need to put in 70, 3600, 699. Right, so 70, 3600, 6099. Let's have a quick look. 4.366. So all I would ask you to do is get an account on Djuli and just follow the demo, just to kind of get a sense of click there, do this, just get that sense of it. I'm not going to say that, now you're off and you can just do what your own thing, but work with us on this. The more of you that are using it, then the more, essentially the better it'll get, because then we can use the feedback. There's a feedback button up here to help us improve it. So I've uploaded the data. I've done it because I say EIS is really good for immunosensors. I've uploaded the data. I'm now trying to analyze the data, and I think I have done everything correctly. So it's now analyzing it. And so I just want to show you. Now, a lot of EIS software is developed for people who are quite interested in things like corrosion. So in experiments like corrosion, there's not really, the concentration of the molecule in the solution is not often as interesting. But with biosensor guys, we want to know how the EIS spectrum is changing as a function of concentration. So we've uploaded the data, we've put in a circuit, and now what the software is doing, it doesn't display it, I would say, in the best way possible, but it's showing here's concentration, here's the value, and so when I look at this, I can see that most of these elements do not have a good correlation with concentration. But one of them actually stands out. It's not bad. I could draw a best fit line through that, and actually I could say that R2 actually had quite a good correlation with concentration. But if I thought, is my strongest signal in W1? No, it's not in W1. Is it in Q1? No, that's quite flat. R1 is in fact, not very good. There's a bit of data down here. That was flat. So it's a little bit. What I'm saying to you is the reason I like EIS is because essentially you get this entire spectrum of data, which you can then extract lots of components from it, and then using this Djuli software I was actually able to extract and look at each circuit element as a function of concentration and see which one gave me the strongest correlation with concentration. Now I'm not saying that Djuli is completely 100% finished, but I think it's quite interesting that we're taking this software in a different direction. We're developing it from the perspective of people who are trying to do biosensor development, whereas actually when you really look at the history of impedance spectroscopy, it's been developed often from applications like corrosion, the software is all slightly biased towards those applications. So open a Djuli account. They're completely free. You can download your own software. You can follow this and at least just get a little bit of practicing going on. And then we at ZP will continue to improve and make it better. So I'm just going to skip through this now because I've done my demonstration. I appreciate you guys doing it. Second question 3 minutes ago. Ali asked an interesting question, what are the challenges for the commercialization? That's a good question. What are the challenges for commercialization of a inline monitoring for microbial content of drinking water? So I like this kind of question because it's commercialization. If you're into biosensors, you should always really be thinking about how can I make this into a product. Biosensing is a very practical science. It can really impact people's lives, so I like commercialization. It's for drinking water. I think drinking water is critical now and will become more critical in the future. So good application, good question. And it wants to do the inline monitoring of it. So the answer to the question is, what I think makes it really challenging actually is, one of the challenges anyway, is that if you look at microbial content, I know we could talk about different regions of the world, but if we were looking at like the US and Europe, for example, the colony forming units, the CFUs, the colony forming units are really low. That's less than one colony forming unit in 100 milliliters. So it's actually the problem with testing clean drinking water is the limit of detection. They're essentially saying there's less than sort of one, let's say, bacterial unit or per 100 milliliters. So that's really the challenge, is actually making something that's sensitive enough. So the question was, how do we make an inline monitor for drinking water? And treated drinking water in the US and Europe actually has a very low CFU per 100 milliliters. So that is actually quite a challenge. But in being asked the question, I would actually say it's easier to measure conductivity, by the way. So if I was trying to make a sensor for measuring the quality of drinking water, I wouldn't necessarily go after bacteria initially. I'd actually go after conductivity, because conductivity is just 2 electrodes and measure the resistance between them. So I'd actually, putting my kind of commercialization hat on, I would say conductivity and things like pH were easier to measure than the E. coli. But the original question did make me take I did some reading around this, because I thought it was an interesting question. And what I did find out was that in some regions, this is really just some scientific work that's been done. I wouldn't call this a product by any stretch. But what they're doing is they're actually trying to measure the tryptophan concentration. So rather than in Ali's question, he asked how do we measure E. coli? And E. coli actually can be quite tough. You have to make an immunosensor for it, probably an immunotype sensor for it. it's quite low concentrations. But in this one, they recognised that, and they actually said, well, there's a surrogate for E. coli, and it's probably tryptophan. And now tryptophan is interesting because tryptophan is intrinsically electrochemically active. So I could see it being easier to make a sensor for tryptophan that was near the well or in line than it was to make the direct E. coli sensor. So the quick answer to the question is, I think it's quite tough to make a inline continuous monitor for E. coli. You could use immunosensor technology, which when we were talking about the carbon electrodes earlier on and turn them into immunosensors, that kind of technology could be used for E. coli. But I thought it was interesting whilst researching the answer to the question that actually tryptophan is recognized by some as a biomarker for bacteria, and tryptophan is actually electrochemically active. So that might be the way about going about it. So unfortunately, it's 8:31 here. I always try to keep just to 30 minutes. So thank you for coming to the ZP Developer Zone webinar. We do them every Thursday at 8 AM London time. Thank you for sitting through another Djuli demonstration today. I just want to encourage people to get those accounts, start downloading our data and uploading and following along, and just getting a sense of click here, do that, build that foundation so that when Djuli sort of really matures, then you can start running with it. Thank you to the questions from the forum. They're super interesting and super relevant. So it's 8:31. I will sign off now. We do another webinar at 8 PM on Sundays London time. So if you're interested in seeing sort of more webinars from Zimmer Peacock, we do webinars also at 8 PM on Sunday time. I realise lots of people in Asia are asleep then, but you can follow them on YouTube later on. All right. So thank you very much. I appreciate it, and hopefully we'll see you guys next week, 8 AM London time. Okay. Thanks very much.